On a Sunday night this July, a mathematician did something that isn't supposed to happen. In a single post online, just 3 short lines of math, he ended a problem that had held out for 87 years. No 100-page proof, no press conference. He simply wrote, and I'm quoting him, "Hello there, the Jacobian conjecture is false." And he thanked 2 friends. One of them was a person, the other was an AI. Within a day, one of the most respected mathematicians alive, Terence Tao, a Fields medalist, about as close to a living legend as this field has, had gone through the whole thing on his own blog and confirmed it. It held up. And within a day, the same headline was everywhere. An AI just solved an 87-year-old math problem. Here's the thing. That headline is wrong. Not a little wrong. Wrong in the one way that actually matters. And the real story underneath it is stranger and a lot more interesting than the version that went viral. Because this isn't a machine replacing mathematicians. It's a glimpse of something new about how discovery itself might work, and about what, in all of this, is still very much ours to do. Let me show you. First, what actually broke? I'll keep this in plain English. Picture a machine. You feed numbers in, new numbers come out. And every machine in this story is built the same rigid way. You're only allowed to add and multiply the inputs. That's the whole toolkit. No looping, no wrapping, no clever tricks. Just adding and multiplying. The simplest one just doubles a number, and it's easy to run backwards. A 10 comes out, you know a 5 went in. The one thing that can ruin a machine is a collision. 2 different inputs that give the exact same output. Once that happens, you're stuck. You see the answer, but you can't tell which input it came from. You can't run it backwards. Now, you might already be thinking, can't multiplying itself cause a collision? Absolutely. Take the machine that squares a number. 2 times 2 is 4. But so is -2 times -2. 2 different inputs, 1 answer. A collision for free. But look at how it happens. To drag 2 and -2 together, the machine folds the number line in half, and the fold leaves a crease right at 0. One spot where it pinches and stops being clean. And that's the pattern behind every collision. To bring 2 inputs together, a machine has to fold, and a fold always leaves a crease somewhere. So here's the natural question. What if a machine has no crease anywhere? Perfectly clean at every single point. No fold, no collision. In 1939, a mathematician named Keller bet that's always true, no matter how many dimensions you add. For 87 years, nobody could prove him right, and nobody could prove him wrong. So, could a machine collide with no crease at all? In principle, yes. Picture a spiral parking ramp. Driving up, you never fold, never crease. It's a smooth climb. But look straight down. A car on the 3rd level sits at the exact same ground spot as a car on the 2nd. 2 cars, 1 spot. A collision, with no crease anywhere. Except the ramp cheats. It loops, it curls around in space. And our machines aren't allowed to loop. All they can do is add and multiply. So we're stuck between 2 dead ends. Squaring collides, but it creases. The ramp stays clean, but it loops. What nobody could build for 87 years was a machine that manages both at once. Adds and multiplies only, yet collides with no crease anywhere. Everyone bet it couldn't exist. Then, this July, someone found the one that does it. And better yet, you can see it for yourself. Here it is, 3 short lines of pure adding and multiplying. This machine is a bit bigger than our doubling machine. It takes 3 numbers in at once and puts 3 numbers out. But the rule is exactly the same. Watch me feed it 3 completely different starting points. Take the simplest line. For the first point, everything gets multiplied by 0, so it comes out 0. For the second, the 2 pieces are equal and opposite, so they cancel out. 0 again. For the third, same thing, 0. Run all 3 lines for all 3 points, and everyone lands on the exact same answer. 3 totally different inputs, 1 identical output. No way back, and not a single fold anywhere. That's the whole discovery, on a single screen. And that's the magic of a counterexample. You don't have to trust a lab or an AI or even a Fields medalist. You can check it yourself. A careful teenager could do it in an afternoon, which tells you the hard part was never checking it. It was finding it, the one machine, hidden in an ocean of possibilities, that threads this impossible-looking needle. And that's exactly why the thing that found it wasn't a person. One honest note: this machine breaks the rule in 3 dimensions and up. The flat 2-dimensional version? Still unsolved. No one yet knows if there's even enough room down there to do it. So the conjecture isn't dead. It just lost a piece it was never supposed to lose. So who did this? Here's where it gets good, and where you have to be careful, because the popular version gets it exactly backwards. It started with a question. A mathematician named Akil Matthew asked a friend to take a fresh look at the old problem. That friend, Levent Alpöge, tried something new. He handed it to an AI, Anthropic's model Claude Fable 5. And it's worth being precise about what the AI did, because this is the whole point. It didn't reason its way to an answer the way a person would. What it's great at is searching. Remember, these machines can only add and multiply, but there are more of them than you could check in 1,000 lifetimes. A human can try a handful by hand. The AI tried staggering numbers of them, fast, hunting for the one that misbehaves. And it found one. Now, the elephant in the room. Alpoge works at Anthropic. The AI is Anthropic's own product. Normally, a company using its own tool to announce a breakthrough is when you should raise an eyebrow. But this is the rare case where you don't have to trust anyone, because we just ran the check ourselves. It doesn't matter who built the AI. Within hours, mathematicians around the world ran that same check by hand, on their own computers, and it held up. And that's where Terence Tao comes back in, a completely separate person. He didn't discover anything. He wrote up a clean explanation of someone else's result, and, being careful, mentioned he'd used a chatbot to help double-check the arithmetic in his own write-up. A different AI, doing a much smaller job. One mathematician summed it up perfectly. The AI, he said, was an inanimate tool in the hand of a mathematician, just like a piece of chalk. A person found this. The machine just helped him look. Now, is this the first time an AI has touched real mathematics? No. Anyone telling you it is selling something. 2 years ago, one of Google DeepMind's systems scored at silver medal level at the International Math Olympiad, the world championship for young mathematicians. Earlier this year, AI-assisted work produced original proofs to several problems the legendary Paul Erdős had left open for decades. Each one checked and formally verified by human mathematicians afterward. This result is the newest link in that chain, not the first. So why does this one hit so hard? Because a famous, named, 87-year-old problem finally fell, and a Fields medalist signed off on it in a day. But keep the honest fine print in view. There's no formal published paper yet. This was verified fast and in the open, not through the slow official review. The flat, 2-dimensional case still stands. And don't confuse this with the flashier headlines from the very same month. Companies claiming their AIs aced that same Olympiad with perfect scores. But those were graded outside the Olympiad's official process, and nobody has independently confirmed them. This one you can check yourself, which is the whole difference. Tao has been clear about where he thinks this goes. An AI can find things humans walk right past, as long as we can keep up with checking the answers. And Akil Matthew, who started all this with a single question, called it a very rapid and very unsettling change. Especially, he said, for younger mathematicians. Hold on to that worry. We'll come back to it. But first, a little history, because we've been here before. 60 years ago, a machine overturned something people had believed for 2 centuries. You've almost certainly seen a small version of this. 3 squared plus 4 squared equals 5 squared. 2 square numbers adding up to another square. And notice, 2 of them was enough. But climb higher, to fifth powers, and Leonhard Euler, quite possibly the greatest mathematician who ever lived, bet it gets greedier. He said you could never hit a fifth power by adding just 4 fifth powers together. You'd always need at least 5. For 200 years, everyone took his word for it. Then, in 1966, 2 researchers set an early computer loose on the problem. The very same move the AI made this year. And it found 4 fifth powers that add up to a fifth power exactly. Euler was wrong. They announced it in a paper famously just 2 sentences long. 2 centuries of belief, undone by a machine that simply searched. Sound familiar? And here's the twist that makes this story sing. For 87 years, the Jacobian problem wasn't just unsolved, it was a graveyard. Brilliant mathematicians kept publishing proofs that it was true. And one by one, those proofs fell apart. It was so treacherous, it once broke a young mathematician named Yitang Zhang. His entire doctoral thesis was built on this very problem, and afterward, his career stalled for years. For a while, he worked at a subway. Then, decades later, he came back and stunned the world with a landmark result about prime numbers. The problem that punished everyone who tried to prove it true was finally undone, in a single evening, by someone who set out to prove it false. So what does this mean for the rest of us? It means a machine can now search a sea of possibilities far too vast for any human to cross. And every so often, deep inside, pull out the one thing that changes everything. That is genuinely new, and genuinely wonderful. But look at what didn't change. A human asked the question worth asking. A human recognized the answer when it surfaced. And a whole community of humans, in hours, made sure it was real. The machine found the needle, but people decided the haystack was worth searching, and then checked that the needle was really a needle. One mathematician watching it unfold put it simply, a great time to be alive. And the honest worry sits right next to that. For a young person hoping to build a life in this field, the ground is suddenly moving fast. But what makes you a mathematician was never being the fastest searcher in the room. It was knowing which questions are worth asking, and whether an answer really holds. The tools just changed. That judgment is still ours. The machines can search now. What we choose to point them at, and who checks what they find, that's still very much up to us.